Oh, I remember. They did and they were hanging out for the well, I was just asking about sacks.
Good seeing you all. Let me first start off by going over the calendar for this week and next, and see if you guys have any questions there. All right, 1 second here.
Why would you do that? Did you practice?
Yes. Carl? Oh my God, did you do that? I do have You guys both play soccer, right? Yeah. Your counter doesn't play through this year.
Who is he playing?
He's fine. You guys want to know which team? I mean, well, Meredith.
Probably.
You're fast. Really fast. You live across country. I did not. I compared did not. So they were. For the season.
So this week we're going to continue with the chapter 3, and I want to do a little bit of recap from last week. I know we had our related race test last Friday, but we did start 3.1 on Thursday, so I'll do a little bit of recap over 3.1, and then we'll go into today's notes, which is with mean value theorem with 3.2. And then on Thursday and Friday, we're going to finish up on this section to get ready for the quiz, which is next Thursday. So first derivative test and concavity. The idea there is that we're going to be using first derivative and second derivative to kind of help us gain information about the curvature of the graph, the slope of the graph, and we can sketch out a pretty detailed graph just by looking at first and second derivative. And that's going to cover the end of the new sections for this assessment. So we will have Monday and Tuesday to review over what we've covered this week and last Thursday. Now, moving forward, I think every teacher is going to kind of make a decision as to how they want Wednesdays to look for their class. So for us, I talked with Mr. Jones as well. The other calc teacher, that we're in agreement that we're going to have Wednesdays to be review days. So no tests, no quizzes, no homework, no new material. We're just going to spend the day to review, but we're still going to be productive during this time. So it's not just going to be you coming in. I'm just going to give you study hall. I want to walk through problems with you. I want to see how you do with specific concepts. I may try to walk around and see how you progress, so I can kind of have a better idea as to where you stand with the topics. But I think for this upcoming Wednesday, it's right before a test, before a quiz, so we'll just use that as an extra review day for our quiz. So I'm still going to hold class. I think we are still kind of waiting from admin to give us more information about Wednesdays, about attendance and things like that. So I think once we gather more information, we'll hopefully that'll be clear before next Wednesday comes around. Hey, we'll have a quiz next Thursday, 3.1, 3.4. I'm in the process of grading your related rates test. I think most of them look pretty good, but for those who need to do recovery, we'll have recovery next Friday for that, either 7 a.m. or 4:30 p.m. And I think I'll be able to give back your quizzes, if not today, then tomorrow, so that you can have an idea whether you need to worry about having to do recovery on your test. So that will take us to the end of next week. After the quiz, we're going to try to finish up on chapter 3. Derivative graphs is kind of a big portion of this course, so it's going to show up on the AP exam as well. So we need to kind of have a good idea as to how to deal with derivative graphs. And once we do that, we're still going to spend maybe another day or two on that. Optimization is another section to go over, but we'll have a bunch of review days because Wednesday, Friday of that week is kind of a short week because there's a PSAT day. This is just going to be for sophomores and juniors. So, but it's only a half day even then, and then freshmen and seniors are going to stay at home. I'm going to get into 5.1. I didn't want to stick a test before election day, so we'll just cover 5.1, which is not on the test, and then we'll have Wednesday review and then Thursday test over chapter 3. Now, once we get past chapter 3, the rest of the month of November, we're just going to try to do chapter 5. So we'll do chapter 5 the rest of November. We'll have a test sometime before Thanksgiving, I think, and then once we come back from Thanksgiving break, we're just going to do a small section on derivatives for trig, and then it's basically review for the final fall exam. So we only have a little bit more to go before the end of the semester. But still need to iron out the details for the upcoming weeks, but at least this week and next week is pretty much set. Any questions that you guys have?
Do you not have a unit 4?
Oh, unit 4, we're going to stick next semester because it's antiderivative. So yeah, we're going to come back to unit 4. We just want to do all the derivatives together, and then we'll save the antiderivative for second semester. But yeah, we'll do that second semester. Okay, any questions? All right, let's do a recap from 3.1. So I have links. I had the PDF links under today's date on my website, and I think I went over this diagram. So I'm going to go over this again. Let's do a problem from the classwork page, so we can kind of hopefully get more solidify our understanding of extreme value theorem, and then we can move on to 3.2, which is mean value theorem. So this is the big idea that we covered from last Thursday. So the big idea with extreme value theorem is we're trying to find the absolute max and min on the closed interval. We're trying to find the highest and lowest points on the graph. Now, obviously, if you could look at the graph, that's not a challenge, right? Highest point, you just pick off the highest and lowest y values. But having to do this without looking at the graph, we may need to do, we're going to have to rely on derivative and kind of more information that is not as visual. So in order to find absolute max and absolute min on a closed interval, the first thing we need to establish is that we can't have any breaks in the graph, right? If we're trying to determine this without looking at the graph, we need to have some confirmation that we're not going to all of a sudden have a hole or an asymptote that's going to mess up our potentially mess up our guarantee of finding max and mins. Because if we had a hole at the endpoint or a hole here, then we can't, right? This is no longer a candidate. So we want to make sure that that our conditions pass. So there's only one condition, and that condition is continuity on the closed interval. We just have to confirm that there's no asymptotes, there are no holes, there are no breaks in the graph. And if we're looking at polynomials, we basically don't have to worry about it. Okay? But if we're looking at a rational function where you see a variable in the denominator, then we have to look for holes or asymptotes or breaks in the graph. But just because we see holes and asymptotes doesn't mean that we'll automatically say that extreme value theorem doesn't apply. We can still have holes and asymptotes, but as long as they're outside the interval, we're safe. Okay. But if there's an asymptote that is right in between our interval, then we'll stop the problem and say, okay, extreme value theorem doesn't apply because our continuity condition cannot be established. Okay, but no need to worry about this with polynomials, but with other rational functions, which I'll probably do an example of each in the next day or two, but that's something that we have to establish. Now, just by saying continuous is not enough. We have to establish the endpoints as well. Not endpoints, the interval. So from A to B. So we need to make sure we put brackets around our endpoints. So our candidates for absolute max, absolute min are going to be endpoints and critical points. So endpoints will always be given to you. You don't have to guess what the endpoint is. They'll be given to you. But we do need to find critical points. So critical points are places where we have slope 0 and places where we have slope sharp turns or slope undefined. Slope 0 and slope undefined can be max and mins on the graph. You can imagine this being the highest point if this was a little bit lower. And this is the lowest point on the graph, even though it's a slope undefined. So in order to find those critical points, we have to go to the derivative. So we find the derivative. Okay. And we set the numerator of the derivative equal to 0, and we also set the denominator of the derivative equal to 0. Now, if you're dealing with a polynomial, there's no denominator to worry about. We just set the derivative equal to 0. But sometimes when you find the derivative, there may be a leftover variable in the denominator for rational functions. If that's the case, you got to set both top and bottom equal to 0 separately. Now, when we find our critical points that when we go through this process, are we going to use every critical point that we find? Maybe, right? But we have to make sure that are located where?
Within the.
Yeah, within the interval, right? Within the interval. If it's outside the interval, we're not going to use it. So sometimes we may spend all the time finding all these critical points, and none of them fall inside the interval. If none of them fall inside the interval, then you're just down to 2 choices, and that's possible where you only test 2 points because there's no critical points between the endpoints. All right, so once we find our critical points and we've established that these are good to go, we're going to take the time to plug them into the original function. Because now we want to know the physical locations of these candidates. So make sure you plug them into the original function and not into the derivative. And when you do that, you're going to get these y values like 1, 5, -3, 7. And once you get to those values, you're just comparing those numbers. The highest number you see is your absolute max, and lowest number you see is your absolute min. The emphasis is on the y value. So some of you may want to put order pairs, but I'm going to require that you guys give me the y values. If you leave the x values out, that's okay. But I want the emphasis on the y value. If you put order pairs, then I'm not really sure that you understand the importance, right? But the y value is more important than the x. So it's like saying what's the maximum height, right? The maximum height, you wouldn't say 4, right? You would say the maximum height is 7. So if we write it out this way, it kind of helps ensure we are putting the emphasis on the y value. Okay, any questions about this process? Let's do one example just to solidify our understanding here. So I'm going to go to the homework. I think I also included it under today's link. If you don't have this, it's okay because it's just one problem. You can just copy this down. It's number 21. We want to find the absolute max and absolute min on this closed interval. So what type, are we going to have any issues with continuity here? This is a polynomial, right? So we're safe. We know that we don't have to worry about any issues with breaks or holes or asymptotes. But we have to make our statement, right? We have to, so how do we say this? Our function is continuous. How do we complete this statement?
On the interval.
Yeah, on the interval. Closed, right? Brackets. Okay, so if you say continuous, that's not enough. If you say continuous everywhere, still not enough. Continuous on the closed interval for this problem. Okay, what's next? What's our next step? So before we find critical points, we first have to find derivative. Okay, so I just want to make sure that we are understanding these steps, right? Derivative is where the critical points are going to come from. So we find f prime, go through power rule, x cubed becomes and this becomes, yeah. There's no denominator to worry about, so because we're dealing with polynomials. And then we just do what? We set the derivative equal to 0, right? We're not going to have to worry about any sharp turns. We're just looking for slope zeros and make sure that we've gathered all the candidates. Okay, I can factor this, right? What's the GCF that can come out? 3x. Solve both of my x's there. Okay. Are we going to always use every critical point that we find? Compare it with the what? Interval, right? Always go back, right? We always want to make sure that we are keeping our focus on the interval, right? We can't assume that every critical point is going to fall between. But are these critical points good to go, though? These are good, right? 0 falls between -1 and 2. 1 is between -1 and 2. So we have 2 endpoints and we have 2 places of slope 0. So we have 4 candidates. And now how do we test those candidates? Plug it into the original, right? Not into the derivative. The derivative will tell you slope, but it's not going to give you physical location, right? We're looking for absolute maximum location, absolute minimum location. So each of these 4, 2 critical points, 2 endpoints into the original function. So we'll say f of -1. We'll find f of 0. We'll find f of 1. And we'll find f of 2. Okay, -1, I plug in here, that's -1 minus 3/2, so -2.5 or -5/2. Okay, 0 in here, and for x, 0 minus 0. Plug 1 minus 1.5, -0.5. I got 8 minus 6. 2. Okay, so now our focus is just with these numbers, right? So what can we say? Absolute max is what? 2. So I don't want you to say 2, 2. I want you to tell me that's the answer. And if you want, you can provide the x value as well. But it's less important. Okay. Absolute min is good. The x value is less important. Again, if you look in the textbook, they're going to say order pairs, but I'm going to emphasize y value because that's what the College Board AP exam is accepting as the correct answer.
So, sorry, I think I just missed this, but like where it says like f of x is continuous at -1, 2, like, is it always continuous or how do you know that it's continuous?
Right now, we're dealing with just easy polynomials, and it's always going to be continuous. But if I had a function where there was a variable in the denominator, let's say I had a function that was this. Then the way that we can determine whether there's any issues with continuity is we set the denominator of our function equal to 0. And that will tell us where any discontinuities are. So in this case, the discontinuity for this problem would be at x equals 1. There's a break, there's a vertical asymptote, and we compare this with our interval. And if the break in the graph is in between the interval, then we stop the problem and we say function is not continuous. But if the break is outside the interval, then we're safe and we can say continuous on the closed interval. Okay. Yeah, good question. But I will look at some of the more involved problems maybe tomorrow or Friday. But I want to kind of just review the basic concept and so that we don't forget about this and we can look at some more involved problems tomorrow. But is the big idea okay? Are you guys good with the? Okay. But yeah, polynomials are nice because you don't have to worry about any of this continuity issue. But if there's any variable in the denominator, we got to do that additional step of, wait, I got to check if the break is going to affect my interval or not. Okay. Let's look at notes for 3.2. Now, you may have printed out this note sheet, which is fine. I just find that this is a little wordy. So to explain the concept, I created a summary sheet, which I also included in your on the links that I had for you. But I figure that if I can break it down into just a picture with some important points, we can worry about the nuances as we later when we look at specific problems. But I want to just kind of get the big idea in your head. For now, we can worry about the details later. Okay, so here's a big idea with mean value theorem. With extreme value theorem, our goal is to figure out the highest and lowest points on the graph. So mean value theorem, there's a different purpose. Mean value theorem, we're not trying to find the highest and lowest points. We're trying to find a location where a specific slope is occurring. So to demonstrate that concept, let me go through this diagram here. Let's say we had a function that's given to us. And let's say that function is a polynomial. And let's say that function is continuous, no breaks. And there's another condition that we have to worry about is now we don't want any sharp turns. We don't want any sharp points, sharp turns. It was okay with extreme value theorem because we're looking for highest, lowest points. It doesn't matter if the graph is smooth or not. But here, because we're trying to guarantee a slope, we don't want there all of a sudden to be a sharp turn that's affecting our condition. So we have to establish our function not only no breaks, but also no sharp turns. But the nice thing about polynomial is that we can just go ahead and write these statements out. We don't do any additional checks. Okay, but we'll talk about these conditions breaking down for other types of problems. But let's just say we have a smooth curve. Okay, we've established we have a smooth curve. Now the problem is going to give you endpoints, and you're going to take those endpoints, and we're going to find order pairs, and we're going to find the slope between the endpoints. Okay, so that's the first thing we do. We plug into the function, figure out what that slope is, and let's say the slope that we found between the endpoints was 1/2. Okay. Now, what mean value theorem is telling us is that once we establish that slope, let's say it's a slope 1/2, there's going to be a guaranteed steepness of 1/2 somewhere between the endpoints that is shared. So if there's a slope of 1/2, there must be at least one point where there's a steepness of 1/2 as well. If the slope that we find is 6, then there must be a slope of 6. If there's a slope endpoints of -10, then there must be an exact steepness of -10 somewhere between the curve. So it's kind of like an intermediate value theorem, but for slopes, right? We know that we can guarantee a specific slope if the slope between the endpoints exists. Okay. Any questions about the concept here? So once we establish what slope we're trying to target, then we're trying to find that specific location where that slope occurs. And then this is where we come to the derivative. So we're going to find the derivative. We're going to use the derivative to find the location. And when we find the location, we found our answer. We found the specific location of that particular slope that we're targeting. Okay, so let me go through the rest of the steps. This is what mean value theorem looks like. F prime is equal to f of b minus f of a over b minus a. So this whole mess is just to get to this slope between the endpoints. So we need to find the slope between the endpoints, but that means we got to find the y values, we got to find the order pairs, we got to go through, it's like a separate problem, basically. But once we can find that slope, then we have this piece of the puzzle figured out. And now we can turn our attention to the derivative, because the derivative is going to help us connect the dots between the slope and the location. So if I'm trying to figure out a slope of 1/2, the derivative function is going to help me connect that location with the slope. So we're going to take the derivative function, set it equal to the slope. It could be 1/2, it could be 6, it could be 9, it could be 3, whatever slope we find. And then we're just working backwards and we're solving for x. For mean value theorem, a lot of times they use the variable c to indicate that as a solution. So a lot of times we're looking for c value. C value is just the x value location of our solution. And the final thing is the solution that we're looking for has to be between the endpoints. Right? If it lands at the endpoint, it's not part of our solution. If it lands outside the endpoint, obviously not our solution either. So the nitpicky parts of mean value theorem, I'm going to talk about later, but basically has to deal with this. Has to deal with the brackets for continuity, parentheses for differentiability, and then our answer has to be on the open interval from A to B. But any questions so far about the big idea, big picture of this problem, of mean value theorem? Okay, let's look at some specific examples. So I'm going to turn back to the notes, and we're going to bypass all the steps here, and we're just going to go to example 1. Okay, mean value theorem. We want to guarantee a slope, a location of a particular slope. Do we have to worry about any conditions breaking down? Okay, what are we looking at here? Polynomial. So we know we're safe. We just have to take the time to write out those conditions. Okay. So let's see if we can write those conditions out. First condition, our function is continuous. Okay. How do I finish that statement? Okay. How do I write out those intervals though? Good. Brackets, right? I know it seems like a minor thing, but AP exam is looking for that. I'll be looking for that as well. If you just say continuous, that's not good enough. If you use parentheses, that's not good enough. You got to use endpoints. And you can't use A and B, okay? You got to specify the location. So a lot of these nitpicky small things that I'm looking for. So we've established there's no breaks in the graph. Okay. What's the second condition? That's right. And we know we're dealing with polynomials, so we know we're safe. But how do we finish this statement? Differentiable. Where? Okay, between the endpoints, but is there a slightly different notation that we have to involve here? Yeah. So continuous is with brackets, differentiability is with parentheses. Right. Seems like a minor point there, but I want to talk about what that means. So this tells us that if there's a vertical asymptote at the endpoints, that's going to affect our interval, and we stop the problem. But if there's a sharp turn at the endpoint, we're still safe because we only need there to be a smooth curve between the endpoints. Right, so that's getting to the kind of like the nitpicky things about this theorem. But for now, let's just focus on the fact that we need different notations for continuity and differentiability. Brackets for continuity, parentheses for differentiability. Okay, so we know that mean value theorem is good to go. Our conditions is good. We have a nice smooth curve. Okay, what's next? What information do we want to gather next? Okay, but before we find the slope, we first have to find, no, before that. Yeah, it's probably an obvious thing that I'm saying, yeah, but before we find the slope, we first have to find the y values, right? Okay, y. So I know for you, it may be obvious, but I just want to kind of have you guys verbalize it. So we need to take the time to figure out the y values. They're not giving us the order pairs, right? We got to find those order pairs ourselves. So how do we find order pairs? Plug this back into the original, right? I know this seems obvious, but I see a lot of students, they want to plug this into the derivative and that just throws everything off, right? So x values go into the original function. Okay, so -2 in for the x's. So I get -16 minus 2, that's -18 plus 4, that's -14. I also need to find the order pairs at 1. And I get 7. Okay, now I can take these order pairs and find the what? Find slope, okay. So slope is just subtracting the y values in the numerator and then subtracting the x values in the denominator, right? So what does that end up being? 7. So this tells us, now is this 7 related to this? difference, just coincidence, right? It's just a coincidence. We're not picking one number over the other. It just so happens that the slope ends up matching one of the numbers that we found. But going back to our diagram, this is what we found. We found that our endpoints has a slope of 7, and now we're going to turn to the derivative to help us locate where else on the curve is there a slope of 7. Okay. So let me write out mean value theorem above here. So this piece of the puzzle we found, this is the slope, and then we found it here. So we have this piece figured out. We want to guarantee a slope of 7. We're looking for a slope of 7. What's our next step?
Set the slope equal to the derivative.
Yeah, so now we look for the derivative. Okay, now we involve the derivative. But the first portion of our problem has no derivatives involved, right? We don't jump to the derivative. We need to gather information from the original function. Okay, so now let's find f prime. Okay, what's our derivative? What's our slope formula?
6x squared plus 1.
Okay, 6x squared plus 1, easy power rule, right? Okay, where does the 7 go in this formula? Do I plug the 7 in for the x? Okay. That's a mismatch, right? I don't want to put slope in the location. The slope is going to go in the slope portion of my derivative. Basically, I'm saying my derivative equal to my slope, right? So the 7 goes here. So the derivative is going to do some work for us, right? Usually we give it an x value and find the slope. Now it's the other way around. Now we know what slope we want, but we want to find the location on the graph that has that particular slope. So now it's just an equation that we're solving. Right? Okay, subtract 1 from both sides. Okay, we need to take the square root of both sides. Now, whenever you take the square root of both sides in the equation, that's when you have to involve plus or minus. So x is equal to plus or minus 1. We convert the x in notation for c, so we say c is equal to 1, and c is equal to -1. Again, c is just a notation that we use for the x value solution that we're looking for. Okay. Anytime we find a solution, we have to check it against the what? The interval. Can we keep both of our solutions? Okay. What's the only solution that we're going to keep? Just -1. Okay, let me go back to the rule here. We're only going to keep the c value on the open interval. So anything that lands at the endpoint is not good enough. That's removed.
Mr. Yang, what if both of the c values end up within the interval?
If they both what?
They end up within the interval.
Then we keep both answers. Okay, we keep both answers. Okay. So we could have two locations, right, where there's a slope of 7 on the curve. Now, what if you go through this process and both your answers are outside the interval? Okay, let's say it's already continuous and differentiable. And then you went through the process and you found two answers that are outside the interval. What would you do then?
You take the second derivative?
Okay, so basically, there's a guarantee of at least one solution. So if you come across a situation where none of your solutions work, or none of your solutions are in an interval, something didn't go right in your process. You got to go back and look at your work. There's a guarantee of at least one solution. So maybe you did some algebraic mistake. So go back and double check that. Or maybe you made a mistake with the calculation here. Maybe you're finding a different slope and that messed up your interval. So yeah, so just want to keep that in mind, that you're guaranteed at least one solution. Maybe there's more than one solution, But after you get past these two conditions, we should never have a situation where there's no solution. Okay, there's at least one. Okay, so we said 1 is not good enough, right? So just -1. Okay, so to recap, mean value theorem, we're trying to find the location where there's a particular slope. Polynomials are nice. We can just make sure that we state our conditions. But then we have to find the first half of the work is trying to figure out the slope. So we got to take the order pairs, plug into the original function, get the slope, and then you find the derivative, and then you set them equal to each other, and then you solve for x. And when you solve for x, you got to go back and compare with your interval and make sure that if there's more than one solution, that they are that they're both inside the interval. Or if there's one solution, make sure that the one solution that you're getting is inside the interval, right? That's also a quick check to make sure that you're on the right track. Okay, any questions here? So over the years, I feel like students just naturally struggle with mean value theorem. And I think the reason why is because there's only one formula, but you can't do this in one step. And I think sometimes we want to rush things and we think we can just do it all in one step, but this requires like 3-4 steps, right? You got to take the x values, you got to find the y values, you got to find the slope, and that's only half the part. Then you got to find the derivative, and then you got to set them equal to each other, and then you got to solve for x, and then you got to compare the interval. It's like 5-6 steps, right? If you try to do it all in just one calculation, it's not enough, right? So I think the process is long, and that's what's causing issues. Okay, there's one more related theorem that I want to go through, and that's called Rolle's theorem. Before we get to that, though, I want to connect it with mean value theorem and just show that Rolle's theorem is it's basically mean value theorem, but it's just a very specific instance of mean value theorem. Now, this slope, this side can be anything, right? It could be 7, it could be 0, it could be -5, it could be 9. Whatever order pairs we find that slope. Whatever slope we find, that's what goes here. But Rolle's theorem is saying, I don't want any particular, I don't want just any slope here. I want a slope of 0. So if I want to guarantee a slope of 0, then I need my two y values to be what? Equal. Okay. So that's really the one additional thing we got to worry about if we want to guarantee slope of 0. I need continuity, I need differentiability, and I need these two y values to be equal. If they're equal, then I know that these will subtract out to be 0. I can set f prime equal to 0, and then the rest of the steps is the same. I'm just setting f prime equal to my slope of 0. So if I want to guarantee a slope of 0, I need my two endpoints to be level with each other, right? If they're level with each other, I can draw a horizontal line between them, and I can guarantee a slope of 0 somewhere in between. So I want to make that connection before I go to Rolle's theorem. It's just basically mean value theorem, but I just want these two numbers to be the same. That's all. Which will force this fraction to be 0. Okay, so here's Rolle's theorem. Same formula as mean value theorem, but now we're looking for a very specific slope. A slope of 1, slope of 2, slope of 5, none of that's good enough. We want a slope of 0. And the reason why we have a specific theorem for 0 slope is because we look for slope 0 more often than any other slope. So a lot of times that's where our solution is lying, is what we want. So because of that, we have a special case. So if you look, the theorem is similar, right? We still want continuity on the closed interval. We still want differentiability on the open. But because we're looking for such a specific slope, we need our endpoints to be level with each other as well. Thank you. So once we find, once we know that these two values are the same, we know that we can set our derivative equal to 0, and then we go through the same process. We find our C value, we make sure our C value is lying between the endpoints. So same thing as mean value theorem, but just a little bit more condition involved on the right side. Okay, let's look at an example. This is back to the notes page, example 2. Okay, determine if Rolle's theorem can be applied. The nice thing is we're looking at a polynomial. Our conditions are going to be safe, right? No issues with condition. But we have to take the time to write them out, though. So continuous where? Bracket 1 to 2. Differentiable. Parentheses, right? Okay. But I want to look for slope 0. So I'm still going to find order pairs, right? So this next step is same as mean value theorem, right? We're going to take our x values, plug into the original function, and get the y values. Whether it's Rolle's theorem or mean value theorem, we need to know what the y values are. Okay, so we plug 1 and 2 into the original function. And this is where I see students make mistakes. They want to plug this into the derivative, and that's not right. Okay, they go into the original function. No derivatives yet. Okay, f of 1. F of 2. All right, what did these order pairs tell us? They're equal, so we can guarantee a what? We guarantee slope 0. F of 1 is equal to f of 2. If we do slope between the endpoints, we're always going to get 0. Now, do these numbers have to be 0? As long as they're what? Good. Okay, as long as they're equal. Doesn't have to be 0. As long as y values are equal. And the reason why I bring that up is sometimes in the problems I selected from the textbook, they all end up giving us zeros. I think when we see it enough, we feel like it needs to always be 0. But as long as they're equal, Rolle's theorem is still good. Okay, what's next? We have our three conditions, right? Continuous, differentiable, endpoints of the same y value. We can guarantee Rolle's theorem. Derivative, okay? Derivative. And we set the derivative equal to 0, okay? There's only one solution, but let's double check, right? Is this going to fall nicely between the interval? Yeah, this is a guarantee, right? So we have to get an answer. There's no such thing as no solution once we get past these three conditions. So we know that between 1 and 2, there's slope of 0. Maybe this is what the graph looks like. The graph may look something like this. Both my endpoints have the same, has a y value of 0. We can guarantee that there must be a slope of 0, and that slope of 0 is occurring at 3/2, or at the x value of 3/2, or 1.5. one thing, I just want to kind of talk about something that I see mistakes with. So first off, any questions with Rolle's theorem? It's just mean value theorem, but we just want the y values to be equal. That's really the only difference. Let me give us a scenario here. Let's say the function, I'm just making stuff up here. And let's say the endpoints were between 1 and 4. Let's say we plug f of 1 in and we get 6. We get f of 4 in and we get 6 as well. We know we're good. We find the derivative, 2x minus 3. And I see a common mistake here. What do you think students want to do? Okay, plug 6. Okay, maybe plug 6 into x. Yeah, set equal to 6. I see that a lot. Like they see this number and they want to set the derivative equal to 6, but it's not. This is not what we want. We want the slope 0, right? So as long as they're equal, we're always going to set the derivative equal to 0. So just want to make sure that we don't lose track of what these numbers mean, right? Okay, we don't want this. This is not what we want. So I've seen it enough times where I'm like, oh, maybe I should start bringing these up for future classes so that they can avoid these mistakes. Okay, so your homework is just with the second page of just mean value theorem. So I have these 5 problems here. So tomorrow we're going to start a new section, but I'm going to use the first parts of the class to do a problem for 3.1, do a problem for 3.2, so we can kind of refresh our memory, even though we're covering a new section every day. All right, those on Teams, you're free to go. Have a great day, guys.
Thank you.
Bye.